Hello, welcome to the explanation video for question number 10 in homework 8. So, this question gives us a normal process, and it wants us to show that if a normal process is y-sin stationary, then it should be strict-sin stationary. So, to solve this question, we have to know what is a normal process is. So for a general normal process, which could be denoted as fx1, x2, and t1, t2, etc. So if we have like n terms, xn, tn, so every term in the process should be defined as xtn. So the normal process could just be represented as 2 pi square root of 2 pi to the power of n times the determinant of the covariance matrix for the multivariate Gaussian process, and 1 over this term times e to the power of minus 1 over 2 times x minus eta transpose times the inverse of the covariance matrix times x minus eta. And we have noticed that since this is a general normal process, so it is just something like a multivariate Gaussian. So the everything here is actually in the matrix notation. So x minus eta is a vector, and we take its transpose, and the C is just the covariance matrix, and we take its inverse. So to know whether a normal process is strict sense stationary or not, we have to look into the covariance matrix. So for a normal process, the covariance C could be denoted as the expectation of x minus eta, which eta is the average or the mathematical expectation of random variable x times x minus eta. So we take the expectation, and this is the covariance matrix. So if we expand this further, so it's the expectation of the whole term. So x minus eta. So here we so here actually in the vector form, this is like we have to take the transpose. It's like taking the outer product of two vectors. So if we write this further down, the first term is just for every set of random variable x from 1 to n, we get xt1 minus the expectation of xt1. So this is the x minus eta vector, and xt2 minus expectation of xt2, etc., etc., till xtn minus expectation of xtn. So the second term is nothing but the transpose of this vector, which just rotate this the first term like 90 90-degree clockwise. So it's something like, let me write down here, xt1 minus expectation of xt2 t1 so xt2 minus expectation of xt2 etc etc, and this is just a vector. So the outer product of these two vectors just forms a matrix, which is the covariance matrix. And if we look further into every single element of the matrix, for example, if we take the first first element, for example, these two, and do further calculation, we could find that this element is nothing but the expectation of xt1 minus expectation of xt1 square. So, which is nothing but xt1 times xt1 plus expectation of xt1 square minus 2 times expectation xt1 times xt1. We just like break the square term further down, and we get these three distinct terms. So since the normal process is strict sense stationary, which indicates that the expectation of xt1 is actually eta. So eta is a random constant here, which denotes the
Apple Music
the average the average of the expectation of random variable x. So by using this property, we could plug eta into the equation, and we will get something like expectation of x t1 x t1 plus eta square minus 2 eta x t1. So if we break down the expectation, so this is variable term and this is a constant term. So the expectation of a constant is just eta square. And for this term, we have 2 eta times the expectation of xt1. But using the property of strict sense stationary again, we also get an eta here. So this term is nothing but 2 eta square. So we could just rewrite the first term in the covariance matrix into something like the expectation of xt1 minus eta square. So this is a general solution, a uniform solution for all the terms in the covariance matrix. So like by using the property of wide sense stationary further, we could notice that this term is actually just RT1 minus T1. So it's the autocorrelation function of T1 and itself. So if we, and this term is just something like RT1 minus T1 minus eta square. And if we like plug everything into this equation, and we could just rewrite the covariance matrix into something like RT1 minus T1 minus eta square, and the last term for the first column would be Rtn minus T1 minus eta square. And the last term in the first row is just Rt1 minus Tn minus eta square. And the last term would be Rtn minus Tn minus eta nn square. So we just rewrite the covariance matrix into this form. So by observing this matrix, this covariance matrix, we could see that the normal process is like stays the same. Like for this process, it won't change anything if we give it like x1, x2, xn. So t1 plus epsilon, t2 plus epsilon, etc., tn plus epsilon. So these are just equivalent, which means this normal process is just strict sense stationary when we observing like it has such a form of covariance matrix. So this just proved our theory, and I think this is the end of this video. Thanks for watching.